Okay, here we begin our next session on principle of virtual work. In the previous lecture, we have introduced how the principle of virtual work is different from the equilibrium equations, and how do we actually apply the principle of virtual work to solve the problems. Uh, Here we brief the steps. So first of all, we identify what are the various external forces acting, and in that process we take all the external loading into account. That may be point load, that may be distributed load, that may be point moments, that may be a force due to gravitation, that may be a force due to a tension in a string, as well as a spring force or any other external loading. Then the next step is to fix the origin or a reference point. A reference point is one which does not move. Okay, so according to the support type of support, we need to make a proper choice of origin. And our next task is to identify the points at which external forces are acting and determine the distance of these points from the reference point, from the point of origin. These points will be given a small virtual displacement in accordance with the degree of freedom. And also we need to take the derivative of the distances which we have computed earlier, and these derivative will actually give us the displacement at each point. Force acting at that point multiplied by the displacement, virtual displacement, will give us the expression for virtual work done due to that particular force. So in that process, we compute virtual work done because of each individual external force or external loading, right? So, and we apply the principle of virtual work as an algebraic sum of all the work done will be equal to 0. Delta W is equal to 0. Please keep in mind that we are specifying that many a times that support reactions or constraint forces do not contribute towards the virtual work. So this is one of the important point which we have to keep in mind. Okay, in order to proceed further, we explain these things through a couple of more examples. So let us first treat an example of this four link problem. So we have a link ACE, ACF, ECB, BD, and DE. These links are connected at pin jointed at C, at B, at D, and F, and it is supported at point A and E. It is important to note that the point E is a hinge joint, while the point E, the support at EA, is a roller joint because it can translate within this slot provided. It means the restriction is not allowed in this direction, in the vertical direction. Restriction is also only allowed in horizontal direction, right? So in order to get the external forces, the first step is external forces. So the external forces here are, or external loads, which is acting at point D, which is an point force acting in the horizontal direction, and at point E there is a movement M acting in the anti-clockwise direction. So you can see the degree of freedom is theta. So when M in the specified direction is applied, the theta increases and the point D will move inward. Point C will also move inward, right? But if the force P is applied, the point D will move outward and theta will reduce. That means the effect of P and M in the provided directions are opposite to each other. Anyway, the concern at this level is we have to get the, as we have decided that our origin is point E, we have to get the point of distance of point of interest from point E. So our point of interest here is D at which the force is acting, as well as E. Okay, so at point D, I need the distance, horizontal distance from point E. So that is what it will be. If I draw a construct a line triangle like this from D to line joining AE, there will be a straight line, and length of that line will give me the XD. So you can see that you can do a simple trigonometry or a geometric construction. So if I make a triangle like this is AC, let us say this point is G. So A in triangle ACG, CG will be equal to L cos theta. Same way, the distance between horizontal distance between C to D is 2L cos theta. By simple trigonometric relations, you can identify that. So XD will be equal to L cos theta plus 2L cos theta. That will make it as 3L cos theta. Okay, the variation of that, that is delta XD, will be equal to minus 3L cos theta into delta theta. So that is how we get the virtual displacement of point D when it is subjected to certain displacement. Okay, so the deformed configuration of the links is as shown here by the dotted lines, right? So if it moves, if M is applied, the theta increases by an amount delta theta, and this xt decreases by an amount delta xt. Since it decreases, it is shown minus delta xt. Okay, now as far as principle of virtual work is concerned, we need to get the work done expression due to all the external forces. Please keep in mind, we have shown here the reaction at point A, the reactions at point E, horizontal as well as vertical, the force, external force at point D, and external movement at point E. Keep in mind that we will treat only the external movement and external force for the principle of virtual work. We will not consider the support reaction at A or the support reactions at B into account for evaluating the work done expressions. ठीक है, तो ये बहुत जरूरी है कि सिर्फ वही पॉइंट्स हमने लेने हैं, सिर्फ वही फोर्सेस लेनी है जो फोर्स एक्सटर्नली एक्ट कर रही हैं, सपोर्ट रिएक्शंस को हम कंसीडर नहीं करेंगे. ओके, अब P पॉइंट पर फोर्स इस डायरेक्शन में लग रही है. So what will be the virtual work expression for the force P? This will be equal to P into delta XD. P into delta XD. Since it will be a negative, so I have written minus here. Again, this M is a something couple. M is a couple, and it tends to produce the angular deformation of delta theta. So work done will be M into delta theta. So M into delta theta minus P into delta XT equal to 0. Please keep in mind that the sign due to M, work done due to M, and the sign due to work done due to P, they are opposite to each other. You can also have a look from the diagram that the tendency of the response of couple M and force P are opposite to each other. So the work done produced due to them are opposite. So we have chosen plus and minus sign here, and delta XD is, we have already evaluated 3L sine theta delta theta. So M delta theta, we get M is equal to 3PL sine theta. So this was what was required, that the amount of couple you have to apply in order to keep this system in equilibrium under the action of force P. Okay, so this is something very, very important in principle of virtual work, that we evaluate the work done due to each individual force and then take their algebraic sum and equate it to 0, since there is no additional work, because no displacement has actually taken place. Okay, So this was one of the example in which we solved using principle of virtual work. Let us now take one more example, which instead of directly applying a force, in a member is connected, which is spring. Okay, so this will actually produce a force. So let us see how we proceed towards this moment, this particular problem. So it consists of two members, two links AB and BC, which are connected at pin jointed at point B. Okay, at joint A and C, it is connected through a spring of spring constant K. The unstretched length of the spring is H. Okay, it is visible from the supports that it is supported at point A and C. But at C it is a roller supported. That means restriction is provided in x-axis, no restriction in y-axis, no restriction in vertical direction. Okay, but at A it is hinge supported. That is, it can move, it can translate, but it cannot, sorry, it can rotate, but it cannot translate in horizontal or in vertical axis. So if we try to look at the origin point, so here clearly our origin point is A. Okay, and the points which will move are C and B. Now the B and C, both the points will have a tendency to translate in vertical axis. Okay, as clear from the forces, the force at point B is obviously in the vertical, so point B will have a tendency to move in vertical direction. The point C, the spring force will act in the axis of the spring, so that is also a vertical force, so the point C will also have a tendency to move in the vertical axis. So therefore we take the distances of point C and B from point A in the vertical direction. So therefore I have taken YB and YC. What is YB? YB is the distance, vertical distance of point B from point A. You can do a bit of trigonometry here. Completing this triangle will lead you to YB is nothing but L sine theta. And in the whole triangle ABC, you can see that AC is nothing but YC, which is equal to 2L sine theta. A simple trigonometric relations will help you obtain the same. Okay, so once you do that, your next task is to get delta YB and delta YC. By simple YB and YC, you can get delta YB and delta YC, and you can see those things YB and YC in this relation. Okay, and once if you give a small virtual displacement, in originally this link is at an angle theta. If you give a certain displacement, this link will rotate further by an angle delta theta, which will create a change of delta YB at point B, and this will also cause a change of delta YC. Okay, now right, so because of force P, the spring will, the spring will elongate. So let us say that is given by S. So from this relation, we can obviously see that YC is equal to H plus S, where H is the unstretched length of the spring. Okay, so we can express S in terms of 2L sine theta minus H, since YC is equal to this much. Okay, so we can compute the magnitude of spring force. Because spring force ka magnitude we all know that it is equal to F is equal to K times X. That is, spring force is equal to spring constant multiplied by the spring displacement. Spring constant multiplied by the elongation of the spring. So you can, by this we can determine what is the spring force, right? Now we know what are the displacement at each point. What is the displacement at point C? What is the displacement, virtual displacement to be precise? virtual displacement at point B, force at point C, force at point B. Next task is to perform the to evaluate the work done because of each of these force. So because of P, it will be P times delta YB. Because of F, it will be F times delta YC. So these are only two terms, but the thing what we get here is the effect produced by P and F are opposite to each other. Means one will contribute towards the positive movement, positive work done, the other will contribute towards the negative work done. So that is why this is P delta YB minus F delta YC equal to 0. We have already computed what is delta YB. We have already computed what is delta YC. We know what is F. P is obviously a non-parameter, given parameter. So by solving, we get a relationship that sine theta must be equal to P plus 2kh divided by 4kl. Everything is known. K is our spring constant. H is the spring length, spring unstretched length, and L is the length of each link AB and BC. They are of equal length, which are given to us. So once we substitute this theta into sine theta into the expressions given above, we can compute what is F, what is the value of F, okay, in this expression. So we can obtain what is the spring force. So you can see here that we could evaluate the forces in the members in the spring without actually performing the free body diagram principles and equilibrium principles. We have implemented the principle of virtual work to solve such problems, and the things get slightly convenient to solve when very large number of elements are there, but the force is applied only at a few points, because the work, we have to compute the work done only for those points at which the external force is acting. Okay, so I think by these couple of problems and whatever we have done yesterday in the previous lecture, the concept of principle of virtual work is very clear to you. Okay, thank you everyone.